Hello, welcome back. Today let's try to do another Leetcode problem, 323, number of connected components in the undirected graph. Let me explain the question a little bit and then go to the whiteboard to explain my solution. Basically, I'm going to use unified. We can see that, it's just needed to check the numbers of connected components in the graph. For example, this one. So how many of them? There are only two. So 0, 1, 2, it is 1. And 3 and 4, that's another one. And let's check the second example. There's only 1. It's straightforward. As we can see, it is connected from 0, 1, 2, 3, and 4. So I'm going to use a unified. For the unified, basically it's a template. But for this example, I'm going to introduce the path compression. It means a little advanced of unified. It will improve the speed. Let me first explain it in the whiteboard about the path compression a little bit, because basically for the unified, you should know the basic template. And then, if you can use the path compression, it will improve the speed. Let's check the example. So if we have for example, 0 connected to 1, connected to 2, and 2 connected to 3. This means the unified is basically array structure. So inside the array from the beginning, so this is the index 0, 1, 2, and 3. So this means inside the 3, we're gonna need to find 2 to 1, 1 to 0, and here is also 0. It means we're gonna use the unified array to find. It's a linear structure. For this way, if you need to find, it is O(n) time, so it really takes the time. But what we are going to do, we just need to compress the path like the balanced tree structure. So the 3 will not connect to 2 anymore. It will be connected to 0 directly. So 0 is the root. And also for the 2, it will not be connected to 1, it will be connected to 0. And for 1, of course, it will be connected to 0. If it is like this way, as you can see, if you use find 3, you got a 0, it will be directly, it is just O(1) time. For this one, maybe O3. And if it is very long, it may be O(n). So this is why we're going to use path compression. For the path compression, we just need to have a while check. So if we take out the numbers, this n not equal to the root. Later on, I will explain the n, because the root, for example, it is 0. And for this n, it will be coming from here. Here will be not equal. N will be coming from 3. If 3 is not equal to root is 0. So we're going to use the path compression. The 3 will be connected directly to the 0. Why? Because, for example, this is next. So the next is UF3, because n is equal to 3. UF3 is 2. So UF3 here is 2, the next is 2. For this next, I'm just using this variable to store the value of 2. Now I'm going to use the path compression. It's this line. So the UF2 will equal to 0. Where's my UF2? UF2 equals 0 means this node 3. Because UF2 is coming from n equals to 3. And UF2 is this number with 3. So this number 3 will be connected to 0 directly. So this means the UF2 connected to 0 and n equal to the next. So where is n? Where is next is 2. So the n equals to 2. As you can see, n equals to 2 from here. So for the next, you use the loop again, and 2 will be connected to 0, and then you use this loop again, 1 will be connected to 0. Finally, this n will become 0. When n becomes 0, you will jump out of the loop. Now let me go to the code editor to finish the coding. So for the unified, I will write the basic unified template, and then we can check the speed together by submission of the code. So the unified will be I for I in range n. As I explained, this is a graph. It started from index 0 to n minus 1. This is why we're going to prepare the UF. And then we're going to define a find function first. So the find, from the beginning, I will write the basic template from the beginning. We're gonna use the recursive function. So we need a tag. So if ufn not equal to n, so just need to return find ufn. Otherwise, if they are equal, we're gonna directly return n. Now we are going to use the union. So for the union, basically we're gonna need two variables n1 and n2. It means two nodes inside of the graph. So this is like an edge. We're gonna union these two edges from n1 to n2. So for the union, directly we can use the uf find n2 equal to find n1. So this line of code means first I'm going to find the parent of n2, this node. What is their parent? And then I'm going to find the parent of n1. Finally, I'm going to put this node connected to the parent of n1 directly. So this is the union. So it means the n1 is the parent of n2 finally. It will be connected like that. Now I'm going to have a tag. So for uv, two vertices inside the edges, I'm going to tag if find u not equal to find v. If I'm not equal, so the result will be +1. From the beginning, I'm going to define a variable result. It is 0. So the result will +1 if they are not equal. So what did I mean by this? The find u and find v are the edges from the graph. For example, here 0 and 1. If they are already connected, we don't need to count the result because finally we're just gonna return the result. If they are equal, we don't need. If they are not equal, it means from the beginning they are not connected. If they are connected, so how many of the connected components, it should be n minus the result, because finally I'm going to use n minus the result. From the beginning, there are 5 components because they are all not connected. After that, if there's one edge connected, so yeah, if they are not connected before, if they are connected u and v, so I'm gonna use the result +1. It means I find one, it is not connected. If I find another one, so the result will +2. Yeah, for example, here 0, 1 and 1, 2, the result becomes 2. And now if there is 0 and 2 connected, it means from here we don't need to plus this result anymore because there are only 2, not 3. So for this one, 3 and 4, we also got a result. It means the result is 3. So n minus the result, it is 2. You can also use other method. Maybe you can use directly the n minus 1. It also works. But now let's just write the union. So if they are not equal, it means I'm going to union them together. So the union u and v. After that, I'm going to use the result +1. This means I find a connected edge. Yeah, it is not connected before, and then it is connected. It means I have a counter, need to plus by 1. Finally, I'm going to return n minus the result. Now let me run it to check if it works. As you can see, it really works. Now let me submit it to check if it can pass all the testing cases. Yeah, as you can see, it passed all the testing cases, but it's not really fast. It is just like 0.1 or 0.2 seconds, and it is like 7% of all Python 3 submissions. Now we are going to optimize it a little bit. And here you can also use other ways. Maybe here you don't need to use this, because anyway you have a n. Yeah, you may use something like this, n minus by 1, because it's basically the same. And finally, you just need to return the number n, because anyway we are giving a number n that is useful for us, because from the beginning we used n, and here there's no influence from the above functions. So let me just run it to check if it works. As you can see, it works. Now let me submit it to check if it can pass all the testing cases. Now let's just check the speed. As you can see, the speed is nearly the same. It's 7%. It means this is also okay. We just save one line of code, save one variable's result. Now let's just optimize. As we know that the recursive function is much slower than the iterative function. Now let me just change this to iterative first. Now I'm going to change this while they are not equal, so n should equal to this UFN. So this is just one change by changing from the recursive to the iterative. But finally, anyway, I'm going to return the n. Now let me submit it to check if we improve the speed a little bit. As you can see, we improved the speed a little bit. Actually, it's doubled. It is 0.1 seconds. Now we are going to use the path compression. So this is something new we need to learn why it is so important to use the path compression. Because if we don't use it, maybe sometimes this file is ON. It is not O1. Yeah. Now let me just make it O1. So for the path compression, I'm going to use a variable n here, going to equal to the root. But inside, I'm going to make it easy to understand. Inside, I'm going to find this root. So UF root not equal to root, and here I'm going to just change this n to the root because I'm going to use the variable n later. So here I have a new variable n. This means, so here this is n equals to the root because I'm going to use this n later. But for the root, it means from here we've already found the root. Now I'm going to use the path compression. So for the path compression, while n not equal to root. From here, you know that if we are going to use this kind of unified way, it means the root may have already been changed. If it has already been changed, it means this n is not equal to the root anymore. For example, in my example, the root is 0, this n is 3. And now I'm going to use this line of code to use the path compression to optimize it. So from here, let me put it here and prepare an empty line. So first of all, I'm going to define a variable next. So the next should equal to the UFN, and now I'm going to update my UFN. So the UFN for this node should equal to the root. And after updating, I'm going to find the new number. My new number will be the next because this next is preparing for the next number. After all this has been finished, it means I've already finished my path compression. From this way, it will become to this way. Now I'm going to run it to check if it really works. As you can see, it works. Now let me submit it to check if it can pass all the testing cases. As you can see, it passed all the testing cases and it's really fast. Now it becomes 0.05 seconds and it's nearly 68% of all Python 3 submissions. Thank you for watching. If you think this is helpful, please like and subscribe. I will upload more Leetcode problems.